All right, good afternoon, everyone. We're going to get back into where we left off last time, talking about triple integrals. I tried to give you kind of a brief overview of the basic idea of an integral in Cal 2, a double integral that we've done, and now leading into the triple integral. And the main thing I wanted you to focus or emphasize last time was this dx, this dA, and what is now going to become our dV, which is the region in which we're integrating over. So our traditional Cal 2 integral, we integrated over a line segment, which was one-dimensional. A double integral, we're integrating over some region in two-dimensional space. That's why we have dA as an area instead of dx, which is like an infinitesimal length. This is an infinitesimal area, a patch of area. And so with the triple integral, our region of integration, the domain that we're integrating over, is going to be three-dimensional. And that means that our differential out here is going to represent an infinitesimal little solid cube, or yeah, I guess you could look at it as a little cube, dx, dy, dz, or dy, dz, dx. You can look at it from 6 different perspectives. That was the main thing before we jump in. And then I also want to point something out that is going to be helpful as we transition away from triple integrals and move into the next sections. All of these together are part of what are called scalar integrals. And the reason we call them scalar is because these functions are scalar functions. Now, I can illustrate that later, but I'm just going to say it for the first time. These functions, f of x or f of xy, or down here, we're going to have f of xyz. These are all scalar functions. They're not vector functions. We studied vector functions earlier in the semester. Those are going to come back later on. And so we will be integrating over vector functions instead of scalar functions. So that's going to bring a whole new class and category of integration for us, because what we're integrating won't be scalar anymore. Okay, so let's get into triple integrals. Let's see how messy this gets. So with triple integrals, we talk about the types of regions we can integrate over. So I said last time, we can visualize the region of integration. We cannot visualize the function itself because it lives in 4-dimensional space. So if we're going to do a triple integral over some region E, then the most basic shape that we can possibly have would be a box. And that would mean that if you look at this box sitting in 3-dimensional space, that when you cast its shadow on the ground, you're going to get a rectangle in 2-dimensional space. So you have that your x's, and this is kind of hard to see, I'll tilt it a little bit. You have that your x values are stuck between, come on. Why am I not writing? It's not letting me write on this. Okay, I'm having a little bit of a problem here. Hold on, let me close this out and see if I can restart it. Oh, it's not even responding. Okay, that explains it. Oh, technology is fun. Got to do a good old-fashioned Control-Alt-Delete real quick. Where is Epic Pen? End it. Okay, let me try and restart that program. Okay, see what happens here. There we go. Okay, so our restrictions, this is our x-axis, okay? This is our y-axis. And so our x's are stuck between 2 constants. Our y's are stuck between two constants, c and d. And notice this is the big thing, our z is bounded between this flat surface up top and some flat surface on the bottom. And so this is z equals some constant, and this is z equals some constant. Does that make sense? So all three variables are stuck between two constants. And for us, we're going to stick with the traditional, A and B is our restriction on X, C and D is our restriction on Y, and we're going to use R and S for our restrictions on the Z. So back to our picture, this would be R, oops, sorry, got them backwards. This would be S, the one on the bottom would be R, okay? So if we have that region, okay, if we have this very nice box, then the triple integral over that box, okay, so the triple integral over that box E of some function of three variables. So that right there, that function of three variables is the thing that we can't visualize. That is that triple integral over that scalar function with respect to volume will be this triple integral. So now, you know how we used to have like an inner integral and then an outer integral? Now we have like an inner, a middle, and an outer. And you can see that the inner integral is this one. That's with respect to z. And we have our limits of integration. And then we have an integral on the outside of that, which is with respect to y, and the limits of integration are c and d. And then we have our very outside integral, which is with respect to x, and that goes a to b. But there are six total. There are 5 other possible integrals. Because these are all constants, we can always change the order of integration. So I'm not going to write all 6 down, or all the remaining 5, but I will do one more. How about if I do this? How about if I choose to go dx, dz, dy? I could go in that order, right? And then my triple integral would start, let's start with the outside one. It would be the limits on y, which are c and d, the limits on z, which are r and s, the limits on x, which are a and b, and then inside, of course, is just the function that we are integrating, right? And then there's 4 more that I could do, just switching these up and, shuffling these around and shuffling the integrals. You can only switch these around if they're constants, if the x, y, and z are between constants. That's the only time you can switch them around. All right, so let's do an example. Evaluate this triple integral over the solid E of x squared y z with respect to volume dv on 0, 2 cross 1, 2 cross 0, 1. And just as before, that's our restrictions on x, y, and z respectively. So I'll go take this over to our notepad and do it here. Are there any questions right now while I'm pasting this in here? No?
I'm a little bit confused by what you mean when you say you can only switch it if they're constants.
If the restrictions on x, y, and z are all between constants.
Oh.
So like this means that x has to be between 0 and 2. The next one means that y has to be between 1 and 2. And the last one says that z has to be between 0 and 1. So do you see, Fabiola, how these are all 3 variables are constrained between constants?
Yes.
Which means that our domain, our region of integration, the solid that we're integrating over, E, is a box. In that case, there are 6 different ways we can do it. So let's go ahead and do this one. I'm gonna go ahead and set this up. It's gonna go integral. I don't know. I'm just gonna go with the standard kind of dz, dy, dx. I'm just gonna choose to do that one, which means that my restrictions on x go first on the outer one, then my restrictions on y, then my restrictions on z, and then the function I'm integrating, x squared yz. Any questions on that setup? let's do the integration because we haven't done one like this yet. Not a triple. We haven't done a triple yet. So let's see how this works. Here are my two outer ones. Okay, now it's time to do the inner integral. So now I need the antiderivative of this in yellow. I need the antiderivative with respect to z. And that means that x and y, both x and y, are going to be treated like constants. And so what would the antiderivative of x squared yz be?
X squared y z squared over 2.
Yep. So the x squared y stays there. And then I have the antiderivative of z, which is 1/2 z squared. So I'm going to write it this way, 1/2 xy z squared. That would be my antiderivative. I just slid the 1/2 out front. Now we're evaluating that antiderivative from where to where?
Z equals 0
0
to
to 1.
1.
0 to 1. And I'm going to put z equals 0 and z equals 1 because I want to make sure that when I'm plugging in 1 and 0, I'm plugging it in for the correct variable. And then, and then that ends my integral there, and I'm going to have dy dx here. All right, let's do this. If we plug in 1 for z, we're going to get something, right? If we plug in 0 for z, it's going to kill everything off. So we should only have one thing left after that. It should be when we plugged in 1 for z, replace that with 1, and all we get is 1/2 x squared y. Do you all agree? Because when we plug in 0, everything goes away. Y dx. Okay, now we're back to the last section. Okay, we're down now to a double integral. So we just do this the way we did last time. So I'll keep going because this one's a real easy one. Okay, take the antiderivative of this with respect to y. And that would give me another 1/2 y squared. So it's going to be 1/4 x squared y squared. And this time we're evaluating this from y equals 1 to y equals 2 dx. Any questions there on how I came up with this? This equals integral 0 to 2. Now this one's going to be a little more involved because I don't have a 0 here. So I'm going to plug in 2, and then I'm going to plug in 1, and I'm going to subtract and see what I get. So when I plug in 2 for y, I get a 4 here, and 1/4 of 4, it goes away, and all I'm left with is x squared. That's nice. And when I plug in y equals 1, I'm just left with 1/4 x squared. That wasn't too bad, right? I can clean this up. This is 1x squared, take away a 4th x squared. That all that leaves me with is 3/4 x squared dx. Now we're back in Cal 2. So antiderivative of that should be 1/4 x cubed. I went ahead and reduced the fraction because I get a 3 down on the bottom, which cancels that 3 out when I do the antiderivative. And then I evaluate that from, I really don't need x equals 0 to 2, but I'm just going to put it here. And when I plug in 2, I get 8/4, which is going to be 2. And when I plug in 0, I get 0. So the answer is 2.
I have a question.
Yes.
Is there some sort of way where we could do it as indefinite integrals? So that way our region can, vary to however we want it to be?
Sure, you could do that. But you're still saying that you would still want these to be constants though, right?
Yeah, we're just gonna assume that they're constant.
Yeah, so you could just use the letters, A, B, C, D, R, S. And so like on this first step, it would make things more complicated because this would be like S here and this would be R. So when
That'd
you
look
plug in
really
S,
messy by the end.
yeah, when you plug in S, you're going to get like S squared. Then you'll still have to subtract when you get R squared, and then you'll have a huge expression. It'll be, doable, but it'll just be nasty.
But there's no way I can just like say forget all constants period and just do a triple indefinite integral.
Yes, but these limits of integration, like since they're not there, okay, let me do it this way. Let me just start with, let me do this. If I just said find the antiderivative of x squared yz with respect to z, right? Here's what you could tell me, that this would be 1/2 x squared y z squared, right? Plus, now you want me to do an indefinite integral, right?
Yes.
So all I could tell you now is not that this is plus some constant. I could say that it's plus some function of possibly y and z. Now think about that for a second. Why is it not just a constant? Because if I take, the whole idea behind the antiderivative is that if I take the derivative of this, right? If I were to take the derivative of this with respect to z, that I should get back this, right? So when I take the derivative of this with respect to z, the 2 comes out, and then you get back this, right? But I could also have had next to this something like any function of x and y. I could have had sine of x plus y here. The derivative of that with respect to z would have been 0. So this would still be correct. But I can't say it's just a constant. I have to say that it could be some function of possibly x and y. Does that make sense, Daniel?
Yeah, that does make sense. So then I can understand why it would become a very large headache to do a triple integral,
Yeah.
triple indefinite integral.
Yeah, because now what you do is you'd say, okay, now I want to integrate that, right? So let's say now I want to integrate that. I'm just going to kind of jump ahead here. So let's say now we go this and dy. So now we do this dy. So yes, you could do this part. This would give you the 1/4 x squared y squared z squared, right? That would give you that. That's the antiderivative of that with respect to y.
Mm-hmm.
Plus, now we're doing the antiderivative of this with respect to y, right?
Yeah, and we don't
But
actually know what that is.
We don't know what it is. So this would just have to stay as the antiderivative of that, right? dy, we don't know what it is. And even if you did know what it was, okay, this right here, let's say that that turns out to be some antiderivative, h of xy, capital H. I wouldn't have just a constant on this one either. I would have some function of possibly just x, because again, I did the antiderivative with respect to y, but it could have x's and y's. So now I have a secondary possible function of x here. That makes sense?
That makes complete sense to me, at least.
Yeah.
So yeah, that just sounds horrible.
Yeah, it would be, but you know, there are ways to do this. We would just have to be given a little more information in order to figure it out. Let me see, I'm trying to think of.
It's probably why we keep them nice and bounded.
Yeah, I mean, for what we're doing, we have limits of integration, so we don't need it. Yeah, it's very hard in general to start with a function of 3 variables and then do an indefinite triple integral and get any answer that's going to be meaningful. I mean, yes, it will be meaningful, but it's just like there's so much unknown, because every time you go take a step backwards, we're not off by a constant, we're off by an entire function of 2 variables, and then when you go back again, you're off by a function of 1 variable. So it's complicated. Good question though.
We had one on one of the mini exams, right, where it was finding the integral, and then it would be the velocity and then position, but then you would know the position and velocity at that time, and then you would just plug it back in and then find out those.
Yeah,
those
kind of like that.
constants.
We would need to know something like that. Now, look, we actually are going to revisit this a little bit later on when we're doing what's called finding the potential function. We'll have to do this multivariable integration like this, and we will be dealing with this. We will talk about things like this. Okay, so we will see it a little bit later, but for now we're doing definite integrals, so we're happy. Okay, let's move on. So look, that's the easiest type of region, and you know, as you should suspect, things aren't going to be that easy, right? So what happens when we have a different type of region where it's not a box? something like a region like this. So let's look at what this is. I'll show you the picture in a second. But let's say our region is such that the x's are stuck between two constants. So x is between two constants, but our y values are not stuck between constants. They're stuck between functions of x. Now that in the previous section on double integrals, we called that a type 1 double integral, where your x's were between two constants and your y was between two functions of x. But now the z value is not stuck between two constants. It's actually stuck between two functions of x and y. So this u sub 1 and u sub 2, those are surfaces, not flat like the previous example. They could have curves to them. So here it is, look. Notice on this picture, the x-axis is the red, the green axis is the y, and the blue axis is the z. So notice here that, again, our x is stuck between two constants, right? X is stuck between a and b. But look at the y values. The y values on the ground here are stuck between some function of x here, this one, and some other function of x there. I'm going to clear this out. If you look at it from the top down, then that looks like a type 1 region from a double integral, right? That's exactly what a type 1 region was. So our x is between two constants, our y is between two functions of x. Now, what about the z? The z is some solid above that. Boom, there it is. Okay. Do y'all see how this is a solid that is above that surface on the ground? And that if you look at it from the top, you can see the solid, right? But what you have to see here is that I have labels here. Here, my restrictions on x are between a and b. My restrictions on y are between these two functions of x. And the restriction on z is between a top surface. So my top surface is this top part of this thing up here. Okay, that's this function. And then my bottom surface is this piece down here, and that's that function. So x between two constants, y's between two functions, z's between two functions, which are surfaces. This is known as a type 1 region for a triple integral. And as you might suspect, the order of integration is not up to you anymore, right? You are strictly stuck with doing it a certain order, just like you were with a type 1 and a double integral. So let's look at what it is. If we have this case, right, then the triple integral over E of some scalar function with respect to volume will be, again, 3 integrals. We have an inner one here with respect to Z, where the limits of integration are those two surfaces. And then you have the middle integral, which is the one that's with respect to Y, where the limits of integration are those two curves. And then finally, you get to the integral with respect to Z, and that's, X, and that's the one that's stuck between two constants. You are not allowed to switch that order around.
Do these have type names as well?
This could be referred to as a type 1. I forget if the book calls it a type 1. No, they don't. And the reason why is I say it's similar to the type 1 because its shadow on the ground is type 1, right? Do you agree that the shadow on the ground is a type 1 region from a double integral?
Yeah.
So that's kind of the only correlation. The reason why, you'll see why we don't have a type name for this in a minute, because there's actually 6 different ways we could do this. So it would become very complicated to start to try and name these.
Why not just type 1 through 6?
Yeah, I know, but it's more, I think what they want is a more foundational understanding. Because look, I'll show you when we get to it. Okay, so there's what we have. So here's our first example. I was trying not to give you the picture of it first. Because I think part of the bigger challenge of this is actually getting the region drawn out properly. Okay, evaluate the triple integral over E of y dv, where E is bounded by these planes. So we have a solid E where these planes create the boundary of the solid. So we need to somehow get our hands around this, our heads around this. X equals 0, that's the YZ plane. Y equals 0 is the XZ plane. Z equals 0 is the ground, that's the XY plane. And this is just a plane. You should recognize that as a plane. The normal vector of this plane is 2, 2, 1, right? Just a reminder of things we know about planes. 2, 2, 1 is the normal vector. Not that that's important, but okay, so here we go. I'm gonna try and draw this. All right, so I have the XY plane. Let's label this X, that's Y, Z. Sorry, I have the YZ plane, which is like this background here. The XZ plane, which is like this side wall here. And then we have the XY plane, which is the ground. And then we have some plane. Now I need to somehow draw this plane. So an easy way to draw a plane, if you're given the plane equation, is just to like let two of the variables be 0. So let's let Y and Z be 0. If Y and Z are 0 in this equation, what do we get for X? If Y and Z are 0, what's X? You get 2, right? So that's like a point, 2, 0, 0. And I could graph that. 1, 2, here's 2 on the x-axis, 0, 0. That's 1 point on the plane. I only need 2 more points. If I have 2 more points on the plane, I can draw the plane. So I'm gonna do the same thing. I'm gonna do let's go x equals 0. So let x and z equals 0. If we do that, what's y?
It's 2.
2 again. So this is gonna be 0, 2, 0. So that's this point, 1, 2, here's 2. So I have that point. And one more, if I let both x and y be 0, then that tells me z is 4. So that's way up here, 4. And once I have 3 points on a plane, I can connect the points together. And that's what I've got, right? This is what I've got right here. So I had the picture of it ready for you here. That's basically what we just got. Okay. And so what we want to do is, this is our region E, right? This is our solid E. We want to see if we can't write this where x is between 2 constants, y is between 2 functions of x. We'll call them g1 of x, g2 of x, and our z is between 2 surfaces, u1 of xy and u2 of xy. Those are 2 different surfaces. So I think, sorry, my computer just is asking me something here. So I think the best way to go about this is to see that the shadow of this on the ground is that region on the ground. And maybe if I draw that in 2-dimensional space, I can start to see my restrictions. So if this is x and y, we knew that this point here was 2. That was that first point here. And then on the y-axis, we go to 2. We have another point here. That's that one. And then we have the line connecting them like this. And then we have our region in here. And that looks like a type 1 from back in double integrals. Hopefully it's evident to you from this that my x's here would have to be between 0 and 2. My y's would be between, well, What are your y's between? Here and here, right? So what's the lower limit?
It's y equals 0.
Y equals 0. And then what about this upper limit?
Negative x plus 2.
Yeah, so this we have to recognize as a line, right? So we have to write the equation of that line. The equation of that line is y equals negative x plus 2. Benjamin's getting that from doing the y-intercept is 2, right? And then the slope is -1. We know it's -1 because you go down 2 over 2, right? So we know the slope is -1. So the upper limit of that is negative x plus 2. Any questions on that? Now, how about the surface though? Because now we need the restrictions on z. Z has to be between two surfaces. And can you all see from our picture what the bottom surface is? That's u1 of xy. And what the top surface is. That's u2 of xy. How about the bottom one? What's that down there?
Equals 0.
Z
Zero.
equals 0, right? That's just z equals 0. So that's just a nice constant 0 function. But the top one is actually the plane itself, isn't it? The plane. And so what we need to do is we need to go look at the plane equation and we need to solve it for z. Because then if we solve it for z, it is now a function of x and y. Right? If we solve this equation for z, then now the right side is some function of x and y, which would be our top surface. So I think I'm ready to put that in here. This is 0, and this is 4 minus 2x minus 2y. Are we good? You ready to set this thing up? We have our limits of integration. We have the integral right here, triple integral over e of y dv. So we're trying to do the triple integral over e of y dv, but that's going to turn into triple integral y. And then we do have to go in the order dz, dy, dx. We have to do that order because our x has the restriction of 0 to 2. Our y goes from 0 to negative x plus 2. And our z goes from 0 to 4 minus 2x minus 2y. Any questions? I'm just going to do the first step because once I do the first step, we get back to a double integral and those you've already done. So I'm going to say that this is the integral from 0 to 2 and then integral from 0 to negative x plus 2. And then now the antiderivative, and I'm taking the antiderivative of y with respect to z, which would be
YZ.
yz. Because y is a constant, right? So yz evaluated from z equals 0, that's the easy one, to z equals 4 minus 2x minus 2y. And then after I figure out all that, I still have to do dy dx. So this will equal 0 to 2, 0 to negative x plus 2. Okay, good news. When we plug in 0, it's going to go away. So I really only have to worry about when I plug in z equals this. So when I plug that in, I get y times, in parentheses, 4 minus 2x minus 2y. And that's it, right? And then I still have dy dx. And now I'm to a double integral. I would distribute the y through, and then I'd integrate. So equals ... You could go the rest of the way.
Now, if let's say like right now y is between 0 and negative x plus 2, if it would be between two constants, would you be able to switch the order?
Yes. Absolutely. If this was between two constants, then yeah, you could treat it like a double integral where well, you couldn't change the first integration. The first integration would still have to be with respect to z.
Mhm.
It would be once you get past that step, then these two, you could flip them.
Okay.
All right. Moving on. All right, now what if we have a solid where still a solid region E. This time our y is between two constants, our x is between two functions of y, and our z is still between two surfaces. So the picture changes a little bit because it's our y's that are stuck between two constants. Our x's are between two functions of y. And our solid here above it is still between two surfaces. So that means that the shadow on the ground is a type 2 region when you look at it in terms of a double integral. So how does that impact the integration? You just have to make sure you do the dy on the outside because that has the constants on it. And that means your x would come in the middle because it's the one between two functions of y. And then your z has to be the very inside one because it's the one that's between two surfaces. So really it's like the x and y, the dx dy switched positions because the y has the constant instead of the x, and then the x has the functions instead of the y.
So it really feels like it's just kind of the same deal.
It
for
is
all
the same,
6 of them.
yeah,
It's just
It's-
knowing which one is the surface.
yep, yep.
If you were to get variables that were bounded by all 3 variables were bounded by functions of x and y, could you change the order around?
No. When you say bounded by functions of x and y, that wouldn't. Let me just think about what you're saying here. That wouldn't be a type of region that we can integrate over. Because now, I mean, that's like I'm trying to think of a shape that would just take a ball of clay and just start mushing it into whatever you want, right? Make it a solid where it's just, some crazy shape out of it. Then if you projected that shadow onto the ground, that region on the ground would not represent, like when you look back at this, right here, if we take this particular solid and we look at it from the top, okay? When we look at it from the top, the shadow of the solid straight down creates that region on the ground. See how the side of this solid is flat and then this is flat, right? I'm saying imagine a solid where the inside wasn't flat. It maybe went in a little bit now. That means that your x's are always between two surfaces, your y's are between two surfaces, and your z's are between two surfaces. You won't be able to do that integration anyway. No, you won't be able to, because you never have two variables fixed between two constants, and so you can never get a definite answer. Does that make sense? You need to eventually at the very end be able to plug in constants for your variables. But if everything depends on two variables, then you'll never be able to do that.
Right, there'd be no solution.
Yeah, there would be. Now, but we know that geometrically there are shapes that are possible that you could have that, right? So what you would probably do in a situation like that is try and break that solid up into pieces that were something like one of these. Does that make sense?
Yeah, I understand.
Yeah, we can definitely come up with solids that are really difficult to integrate over, right? But we have to start off somewhere, right? And this is kind of like the beginning of it all. Good questions, good questions. Okay, so what we'd like to do now, I've kind of lost my spot. Here's where we were, all right? So what happens, the integral, we change the order, right? All right, so look at this problem here. So evaluate this triple integral over E of x, z, dv, where E is the solid tetrahedron with these vertices. So I put these vertices here. This is the point 0, 0. This is the point 0, 1, 0. Oh, wait, sorry, no, that's not 0, 1, 0. This is 0, 1, 0. This is 0, 0, 0. This is 1, 1, 0. And this is 0, 1, 1. So we want to evaluate this triple integral. This is X, this is Y over here, and this is Z. Isn't this a lot like the last problem?
Yeah, it's pretty
What's
similar.
what's kind of different about it?
We have to find the functions.
Yeah, we don't know that we are not given the surface, are we? But do you all see that we do have, like, on the ground in the XY plane, do you see that we have that on the ground? And so we can kind of go over here and we can draw the XY plane. And we can draw that blue thing. It goes like this. It goes over one and over like this. So you have to look at these points to know, you know, this hits up here at 1. This is at 1. Y'all following me for this? Now, do we want to look at this as a type 1 region or type 2? In other words, can we look at this as X is stuck between two constants, Y is between two functions of X, or can you do it the other way where Y is between two constants and the X's are stuck between two functions of Y? It's up to you, right? I mean, in this case, it's up to you. So since we have not done one like this, I'm going to look at this as our X's are stuck between two functions of Y, and our Y values are stuck between 0 and 1. So my Y is stuck between 0 and 1. Do y'all understand that? What about the X's? What are the X values stuck between? So the left side is what? X is
0.
0, okay. And then what about the right side? Be careful over here, stuck here. What is that? What is that equation of that line?
Y equals X.
That's Y equals X. So what am I going to put here?
Just Y.
Just Y, because this has to be a function of Y, not a function of X. So we don't want to put X here. And then this is the part that's, I guess, a little tricky. Z, I don't know if this is tricky or not. We have the top of the surface, which is this one, U2 of XY. And then the bottom of this thing, which is just U1 of XY, which is 0 again. We had that earlier. It's the bottom of it. So I know it's 0 here. But what about the top?
Gotta find the equation for that plane.
How?
Cross the vectors from 3 of the points.
Yeah, so this goes back to the beginning of this class. If we have 3 points on a plane, we can always find the equation of the plane by taking 2 vectors on the plane and crossing them to get the normal of the plane. Right? Remember all this? So what I'm going to do here is I'm going to pick this origin point as the point that's on my plane because it's a nice point, 0, 0, 0. This vector here is the vector 1, 1, 0. And I'm going to take another vector on the plane, which is this vector here, which is the vector 0, 1, 1. And now I'm going to go find the normal vector. So to find the normal vector, I have to take 0, 1, 1 and cross it with 1, 1, 0. And I did this many times before, where I did it with like IJK, and then I like covered up the I's and did my little determinants and stuff. So I'm just going to do this quickly. If I cover up the I, I go 1 times 0, 0, then I take away 1, so I get -1 for the first component. To get J, I get 0 minus 1, but then I change the sign, so this should be +1. And then the last component is going to be 0, -1 again. That's my normal vector. So that's my normal vector of my plane. And so when I write the equation of the plane, it'll be -1 and then x minus something and then plus 1 times y minus something and then minus 1 times z minus something and then equals 0. But what is the point that I'm going to use?
The origin.
Yeah, let's do the origin because the origin's easy, right? This is just 0, 0, 0. And so that should at the end of the day give you -x plus y minus z equals 0. That's the equation of the plane. And so I solve that for z and I get z is equal to -x plus y. So that's going to be my upper limit of integration. Okay, I think I'm ready to set it up. I'm going to do it up here. I'm going to go integral 0 to 1. That's my restriction on y, so I'll put dy out here. Then I'm going to go integral from 0 to y. That's my restriction on x, so I put dx. Then integral from 0 to -x plus y. That's my restriction on z, so I put dz here. And then the integrand, the thing I'm integrating, is x times z. That's the setup. I'm not going to work that out. I'm just going to leave that there. Are there any questions? I'll put that back up in a minute. Paste it in here. Okay. So I think personally that a lot of this is just getting the setup right. You know, once you get the integral set up, then it's just mechanics after that. So everything we've done so far, we were looking at a solid where the x's were between two constants, y was between two functions, z was between two surfaces, or y was between two constants, x was between two functions, and the z was between two surfaces. But there's nothing that says that we can't have a solid where the shadow or whatever is actually being projected on a different plane. So like you could have this, where notice here your y's are between two constants, your z's are between two functions of y, and your solid is actually coming out at us like this. You'll see how that solid right there is perfectly valid in terms of the y's are between the constants, the z's are between two functions of y, and the x's are between two functions of what? Not x and y, but y and z. So you can make it look like the old case if you flip it over like this. And this is what we were doing, right? It was like that. But now I'm telling you, this is the y-axis, this is the z-axis, and this is the x-axis. So everything gets kind of reversed.
Doesn't that mean we could just like pick a shadow?
Well, you can't pick an arbitrary shadow because think about, Terrence, think about what the shadow of this solid would look like on the ground xy, the xy plane. Do you see that the shadow of this down on the ground, if we looked at it, the y's would be between two functions. I mean, sorry, the y's would be between two constants. Do you agree? The shadow of this on the ground.
Right. Yeah.
Now, would the z values be between two functions? So think about this way. Are the z values between two functions? Maybe you come at it from the side. I'm sorry, the x values. You see that the X values here vary?
Oh, yeah. Yeah.
So the shadow on the ground would not be correct as a region because the shadow would be a shadow, but it wouldn't make up for these little undulations in the surface. That's why I was saying it's very important to understand these sides of this solid are like straight. And that way, when you look at it from here, you get that region. Is that making sense, Terrence?
Yeah.
Depending on the solid itself, you may or may not have the ability to project it onto different planes. It depends on the solid. Like what if it was a tetrahedron, like the previous example? That right there. Could we look at the shadow of this on the XY plane on the ground? Sure. Could we look at the shadow of this on the YZ plane? Sure.
Yeah.
Yeah. What about the shadow of this on the XZ plane? What would that look like? You project this shadow over here. That would work also.
Mhm.
So with something like this, you could do it 3 different ways. You could go projecting to the ground to either one of the walls. That's why this starts to get complicated, because for each projection, right, if you project down, you've got type 1, type 2. You project to the side wall, you got another type 1, type 2. The other side wall, you got another type 1, type 2. And we haven't even talked about this. What if you have polar? What if your shadow is polar, right? Okay, but we're not going to do it yet. It's coming. It's coming, not yet though. So that's why I think it's more important to understand the fundamental idea here. So for here, what happens to the integral if your y's are between constants, your z's are between 2 functions of y, and your x's are between 2 surfaces? Well, again, the order of the integration matters. All right. So that's exactly the problem we just did. Okay, that problem right there is the problem we just did. Right? But now I'm asking you to look at it with the shadow on the other 2 planes. So I'm going to paste this in here. See if we can't. Let's see if we can just squeeze the answer in here. So if we take this shadow, this was the shadow on the XY plane. Let's try and do the same tetrahedron, but let's do it on the YZ plane. So think about that. Here's the YZ plane right here. What would the shadow of that object look like on the YZ plane? So if this is Y and this is Z, we have a point at the origin, right? We have this point right here. And then we have this point up here, which is, be careful, that's up here, right? And so we get this triangle like this. I'm hoping that you're seeing that it's this picture, but we're looking at it. I can't get quite what I want there. It doesn't look like a right triangle, but in reality it is. Yeah, okay. I'm looking at that triangle right there on the back side. All right, so from here, I can say my y's are between 0 and 1. And be careful, z's, right? Z is stuck between 2 functions of y. What are they? So what's the bottom of this? Always 0, right? Always 0. And then what is this? What is the equation of that line?
Y equals Z.
Y equals Z, right? Or Z equals Y, because it's got a slope of 1. And so the Z is stuck between 0 and Y. The last thing to do is to figure out what are the restrictions on X. And so when you look at this thing, remember we were looking at the top and the bottom? We're now looking at like this front side here, but we need it as a function of Y and Z. And then the back side, which we need, have these backwards. The function of Y and Z. So what about this? What about the backside? What is that?
0.
0. And what about this front side?
We have to find the plane again.
Yeah, so what was the plane? Because we already went through all that work. Wasn't it negative X plus Y minus Z equals 0? What are we going to solve it for?
X.
For X. Good. Because you want this to be a function of Y and Z. So if you solve that for X, you get Y minus Z. So that's going to be your other surface. So sorry, I'm kind of all over the place here. This is going to be 0, and this is going to be, what did I say, Y minus Z? And then we set the triple integral up again. Okay, we go and we do this integral again. The triple integral over E of xz dv should be 3 integrals here, starting with the y because it goes from 0 to 1, then the z, which goes from 0 to y, then the x, which goes between 0 and y minus z, and you're integrating xz. That's the integral if you were to project that shadow onto the YZ plane. Questions? What about the XZ plane? If we take this, the XZ plane is over here. That's your X, that's your Z. The shadow of that over here is this, right? So if I were to look at that, and this, you have to be really kind of careful with this. Here's XZ. Remember, this is the positive direction on X, that's the positive direction on Z. So it's almost like we're looking at this region from that point of view, from that side. That's why I didn't draw it. I'm not going to draw my region like that, because I'm looking at it as if I were standing on this side over here, looking towards this. This will be 1. Oops, that won't be 1. That'll be erased. Hey, where'd you go? Okay, this will be 1 here and 1 here again. And then we have our, like this. Okay, that's this right here. This is going to be Z equals X. My X's are stuck between 0 and 1. My Z is stuck between 0 and X. That's my Z stuck between 0 and X. X is between 0 and 1.
Isn't that a 1 minus X as an equation?
Yeah, I don't know why I did that. Sorry. 1 minus X. Thank you. Why did I do that? I'm not sure. Losing it. Okay, what about the Y? The Y is a little bit tricky. The Y is probably the trickiest part of this. Because when you're looking at this, here's the shadow. You should have a bottom of your solid and a top of your solid, right? Can someone tell me what the top of the solid is?
It's y equals 1.
Yeah, it's this surface right here. That's the top. And that's the Y value is constant at 1. And the bottom of that is, or the part to the left, is the plane equation solved for Y. What is the plane equation solved for Y?
X plus Z.
X plus Z. I hope that makes sense, everyone. I have to erase some stuff. Basically, the reason why this is on the bottom and that's on the top is because if we kind of rotate this around like this and look at it like this, you can see that the top of this thing is where y is 1. And the bottom of it is the plane, right? Which is why the plane equation goes on the bottom this time. And then we set up our integral. So I think you could do that yourself. I'm done with this problem. Any questions? So we
Are
just
we-
did that. Go ahead.
Are we skipping how to solve them because you want us to just learn how to write it down? Or
I would definitely practice solving them just for your own, like, so you know how to do them. I'm not doing them because of time.
Okay, yeah.
Yeah, I just don't have the time to go through them. They're tedious. And really what it comes down to really at the end of the day is like, you want, as an engineer, whatever it is you're doing down the road, you want to be able to take the problem and convert it to the math. Once you get it to the math, you have plenty of tools out there to help you do the math. So you got to make sure your integrals are set up properly. So focus on that as being your priority, and then the evaluation just being something you should know how to do. Okay, so here we go. Why don't I give you a minute to look at this yourself? How about I give you, I don't know, a couple of minutes. I'll give you like 8 minutes. See how far you can get in 8 minutes with this. Do you all want to break out, or you want to all just stay here? It's up to you.
Just stay here.
Stay here? Okay. Y'all can talk to each other, I mean, if you want. I'll just kind of stand by. And just set up the integral. You don't need to go through and evaluate the whole thing. Just set it up. We'll go just another minute or so. If you got it, then I challenge you to try and see if you can do it by projecting the shadow onto the YZ plane. Okay. So let's talk about this. I'm going to put up what I got as an answer first to see if you got the same thing. Integral 0 to 1. Integral 3x to 3. Integral 0 to the square root of 9 minus x squared of z dz dy dx. So if you got that, then you got the same thing I got. If you didn't get it, then maybe you're right and I'm wrong. We'll see. Let's work through it. So I think the most important thing is to understand how to draw the solid, right? Like if you can't draw the solid, you're going to be kind of stuck. So let's try and wrap our heads around this. Our solid E is the solid bounded by the cylinder y squared plus z squared equals 9. So we should recognize that as being a cylinder with radius 3 that comes down the x-axis. So three-dimensionally, if this is x and this is y and this is z, if I go to 3 here, and let's say 3 here, and -3 down the other side, but I'm supposed to be just in the first octant. So my cylinder comes like this, comes down like this. I'm just trying to show you like part of the cylinder. It's not the whole thing. Like part of the cylinder in the first octant. I mean, really it goes like this and, you know, comes down the whole way, but I'm only drawing the part of it that matters, which is the part in the first octant. So there's that. X equals 0 should be the YZ plane. So that should just be this backside. Okay, that's this backside here. Z equals 0 is the ground, which should be this bottom side right here. Now it keeps going forever. Okay, it keeps going that direction forever, but that's the ground. And then the very important plane, y equals 3x. So I think what would help is if I draw the ground over here. So I'm only drawing the ground here. We have 3 here. We know that the cylinder kind of comes across like this. We've got that back red piece. So I'm drawing this line right here is this. And then this line right here is this. And then now I need y equals 3x. I'll do that in green. Y equals 3x starts at the origin, has a slope of 3. So it goes like this. And that hits here at 1. Oops. But remember that plane, that's a plane, so it's coming out of the page. So on my picture, it goes like this. It continues, right? Goes in both directions, but it goes up also. So when it goes up, it cuts through the cylinder and creates this like wedge like this. Now I realize, you know, your drawing may not be as good as mine, or might even be better. It just, you know, depends on you. But do we all agree that that's the solid we're talking about? You know, any questions on that? So the ground here, the part in gray, that's this over here. And to me, that looks like a type 1 region in terms of its shadow. And so I can see that my X's are between 0 and 1. I can see that my Y's are bounded between, well, this green line, which is 3x, and this top line right here, which is the cylinder part, which is just 3. And so the Z's, I just need to figure out what those bounds are. So I need to look at this surface, and let me see if I can grab a different color. Yeah, I'll do this light blue. So this right here, oh, that didn't work very good. This right here, this top piece, that's like my U2 of XY. That's a top surface. And then the bottom surface is just the ground. That's U1 of XY. I know that that's 0 because it's the ground. So how do I get the top surface? Well, it's the cylinder, isn't it? It's the cylinder equation. That's the part that's that curved part. So I need to take the cylinder equation and solve it for Z. And if I solve that for Z, I get square root of 9 minus x squared. And I'm taking the positive on the root because the negative would give me the bottom of the cylinder. So the top is the positive. So that's where I get my limits, my limits of integration for my Z. Questions, comments, concerns, complaints, gripes?
Where did that x squared come from?
Oh, wait a minute, that's y squared. Oops, thank you. This is y squared. I don't know why when I wrote it down, just in my mind, I brought an x squared over here. Okay, now do you agree? Yes, okay. And then we could go through and do this integration, even though that would not be fun to do. In fact, I wouldn't even recommend you try it. At least we have the integral set up. Okay. Now, I said I challenged you to maybe do the same problem, but instead of doing it where we're projecting the shadow down to the XY plane, try and do it where your shadow is in the YZ plane. So let's take a look at what the shadow would look like on the YZ plane. And you know what, I'll take a second to redraw it. I think that's good enough. So if we're looking on the YZ plane, then we have this, right? And when I look at that, I'm like polar, right? I'm thinking polar to myself because that's just a perfect polar region, right? If I did polar, then I would say, all right, I want my theta to go between 0 and pi over 2. And I'd want my radius to go between, well, it would be everything that would get me everything in here. And this was, I think, 3, right? Wasn't it 3? Yeah. So my radius would go between 0 and 3. But keep in mind, I'm in the YZ plane. And that's critically important right now because this means, you know how our normal polar regions go like this. X is R cosine theta. We replace X with R cosine theta. We replace Y with R sine theta. That's our standard polar. But if we're working in the YZ plane, then we're actually going to make the substitution Y is equal to R cosine theta and Z is equal to R sine theta. Very important. Very important there. We'll deal with that a little bit more here in a second. Let's take a look at, we need now, this is kind of going to give our restrictions so that we get this region in the YZ plane. We need to now look at this, this like front surface right here. And then we need to look at the back surface on the back there. And so the back one would be U1 of YZ, not XY. And this front one here would be U2 of YZ. So can somebody tell me what the back side is of this?
Is it 0?
It's 0, right? It would be X is 0, wouldn't it be? X is 0. And then this one right here is, okay, so we need this, don't we? We need this plane, but that's a surface, isn't it? Isn't that a surface? What is the equation of that surface?
When I solved for it, I got a plane called negative 9x plus 3y equals 0.
Negative 9x plus 3y equals 0. You said negative 9x plus 3y equals 0 is what you got. Did you do vectors and stuff?
Yeah.
Okay. So basically, what you're telling me from that is that y equals 3x is what you're telling me. If you just move the 9 to the other side. If you move the 9x to the other side.
Yeah.
So you actually had this equation because that was the other plane, wasn't it? So without really doing, you didn't have to do the vectors is what I'm saying. You could have just realized that that surface right there, that blue surface, is just the plane equation y equals 3x. And we need to take this and solve it for what? Y or x?
For x.
For x, because we want this to be a function of y and z. So we solve it for x and we get 1/3 y.
I know I saw a plane and I saw 3 points, so I did the.
Yeah. So you just started going, yeah, I get it. It's all right. You got the right answer. Okay, so here we go. This is where things are going to get a little bit weird. All right. Let's talk about this triple integral. This triple integral, I've switched. I know I'm going to be going dx. I'm going to be going dz and dy. Now, why do I know that? Well, because I was working in my shadow is in the YZ plane. Okay. And so this right here, my y and z have to be on the outside. And then the x is because the surfaces were both functions of x. So that's the inner one. And we're doing a triple integral over e of, what was it? Z, right? Like this. Go with me? But I'm going to go to polar. Okay. I'm going to go to polar, which means that I'm going to go integral and let's see, theta is between 0 and pi over 2. R is between 0 and 3. The x coordinate is between, oh, we never put it down, did we? Oh, no, yeah, no. We never put it down. It's between 0 and what?
And 1/3 y.
1/3 y, right? So I should have put that right here. Z is between 0 and 1/3 y. Okay, so this is between 0 and 1/3 y.
You mean x?
We solved it for x,
Yeah.
right?
So it's between x is between 0 and 1/3 y.
the X, oh, yeah, X here, sorry, you meant X here, yes? Is that what
Yeah.
you're saying? Yeah,
Yeah.
okay, yeah, sorry, I meant to say X. And then we have Z, and then check this out, R, dr, d theta, d, sorry, R, let me do it this way. R dx dr d theta. Okay, so what's happening here is that because we went to polar, we have to put an R in here when we put in the dr, right? It has to be there. And on this first integration on the inside here, R is going to be treated like a constant, so that's okay. So then what I can do is I can make one last substitution. Anywhere I see a Z, I replace it with R sine theta. Because of my polar. And let's see, anywhere I see a Y, I replace it with R cosine theta. I forgot that right there. So this goes from 0 to 1/3 R sine theta. Oops, cosine theta. And this is R sine theta times R dx dr d theta. So you'll first integrate this with respect to X, which would just be all of this times X, right? Because this is all constants right now. Should I go through this? Maybe I should. What time is it? 26? Let me run through this. This will be integral 0 to pi over 2, integral 0 to 3, and then the antiderivative of this with respect to X would just be R squared sine theta X evaluated at X equals 0 to X equals 1/3 R cosine theta dr d theta. So when I plug in 0, it's going to go away. That's nice. But when I plug this in, I get something new here. So I get 0 pi over 2, 0 to 3. Let's see, replace X with this. I'll get 1/3 R to the 3rd sine theta cosine theta dr d theta. Are y'all still following me here? Place that X with this, bring the R's and the constants out. I'm okay with integrating this with respect to R. How about you? It's not too bad. The antiderivative of that with respect to R, you get a 1/4, so 1/12 R to the 4th sine theta cosine theta. Evaluated from R equals 0 to R equals 3 d theta. I like this. I plug in 0, it's going to go away. So I just need to plug in 3. 3 to the 4th power is 81. So 81 over 12. Oh, I forgot. This is pi over 2. Sorry, pi over 2. 0 to pi over 2. 81 over 12. That reduces, doesn't it? But I'm not really concerned about that at this point. Cosine theta, d theta. That integration is not bad because I can just do basic U substitution. Just let this be U. And then the derivative, it's right here. So the antiderivative of this should be 81 over 12 times 1/2 sine squared theta. Do y'all agree? Antiderivative of this would just be U squared, 1/2 U squared. So if you take derivative of this, 2 comes out, and then sine theta and then cosine theta. So you get that. Evaluate that from 0 to pi over 2. And when I plug in pi over 2, sine of pi over 2 is 1. So I'm just going to wind up getting, what is this? 27 over 4 times 1/2 times 1. And then when we plug in 0, sine of 0 is 0. So I'm just going to get 27 over 8. I think that might have been a little harder to do it that way, to project it along, and go polar, but it can be done. So curiosity has got me right now. This other integral that we didn't do, where was it? That one right there, we never did that one, right? So I'm gonna go and I'm gonna ask, let's ask Wolfram Alpha to do this. Let's see if it'll do it. So what happens if I say integrate, integrate, integrate? So I'm gonna do like a triple integral. So what am I integrating? I need some more space here. Hold on. So the inter thing is z, right? Z. I'm not sure how Wolfram Alpha is going to do this. I have a different idea. Because of time, I'm just going to do it in here because I know how to put it in easily here. There's probably something online that y'all know of that you can do triple integrals easily. I have my computer, so that's why I can just do it here.
There's a website called Symbolab that does it pretty
Symbolab.
easy.
Yeah, you can just type in the, where is mine? There it is. Okay, so here we go. Okay, so I've got integral. I'll make this bigger so you can see it in a second. Integral. Integral. Close it out. Let's make this big. All right, so we went from 0 to 1. We went from 3x to 3. We went from 0 to the square root of 9 minus y squared. Good thing that was caught earlier. And then we're integrating z with respect to z, then y, then x. Come on, baby. Yes. That's good news. That's good news. Good, good. So we got the same answer that we did doing it the other way. Now, I didn't do that integration by hand, right? I didn't do this. It might be that that would be a very difficult integral to do. I mean, the computer did it like that, but it might turn out that, going to the polar and projecting it on the other plane made the problem doable by hand, where this way, maybe it's not. Did anyone try this one by hand, the one up here? I'm thinking you'd probably have, well, no, it's going to be a basic U sub, I think. Not just basic. It should, yeah, I think it's going to be basic. Because the antiderivative of this is just 1/2 z squared. And then when you replace that with the square root, it'll get squared and the square root will go away. So you won't have any square roots to deal with anymore. Then everything is just polynomials. So yeah, I think it'd work out nice. Okay. How are y'all feeling? Yeah, I know, Terrence. All right, so blah, blah, blah. So, we know how we can cast shadows on the YZ plane. You can do it on the XZ plane. We're not going to go into that. Okay, we have one major result here. Well, we have a lot of major results, but this is a big one. And I gave you something similar to this before. When we were talking about double integrals over some region D of 1 dA, I said that that was the area of D. That was something from last time or 2 times ago. So everyone needs to know that if you're trying to find, if you want to find the area of D, you just need to do the double integral of the constant 1 function with respect to area, and that answer will give you the area of D. We have something similar for triple integrals. If you do the triple integral over E of 1 with respect to volume, that just gives you the volume of E. So if we go to that problem we just did, okay, here's the problem that we just did, but I'm asking you a different question. I'm saying find the volume of this solid. So I give you the cylinder, the planes, and everything else, and I just want to know its volume. Then all you're going to do is go to this setup right here and replace what with what? So this is the original problem, right? So all I have to do is replace that with 1. And that would give me the volume of that solid. Questions or no? And just for the sake of you seeing it, the volume, if you did on the computer, the volume is 3. Okay, as I said before, last class, I said that, you know, when it comes to double integrals, we can do applications. And one of the things you can do with double integrals is find the center of mass of an object, of a lamina. Now we extend this into 3-dimensional space. And it basically says that if you have a solid in 3-dimensional space, a solid E, and you want to find its center of mass, where that center of mass is, wherever it is, where this solid has non-uniform density, which means that the density within the object changes throughout the object, then as long as you're given the density function, then you can always, 1, find the mass of it by doing the triple integral over E of the density function. So you take the density function, you do the triple integral over the solid, and that'll give you the mass of the object. Then you can find the 3 moments. So just like what we did in last class for the moments on a lamina. Because it's 3-dimensional, you have 3 moments now instead of 2 moments. You have 3 of them. So there's 3 different triple integrals you have to do. And then the center of mass is just going to be the center mass is a point, x bar, y bar, z bar, is just each of these moments divided by the mass number that you get from that. Which means that if you want to find the center of mass of a solid that has a density function that's given, you're going to have to do a total of 4 triple integrals. The 3 moments along with the mass. And then you can calculate the center of mass. And then similarly from last time, you can also calculate the moments of inertia. And the moments of inertia are these 3 triple integrals. So you have a moment of inertia about the x-axis, y-axis, and z-axis. So this is just like, I'm not going to go through anything on this. I just want you to know, like, now that we know how to do triple integrals, kind of, you know, here's an application of it. That's it. That's the end of this section. All right, so let's, we're almost done. Let's talk about where we are in the class. So we just finished triple integrals, and today we are supposed to finish triple integrals in spherical coordinates. So we are still like officially 1 week behind. I was talking to one of your classmates after class last time about like, how are we going to reach the end of the class? And remember, there were no in-class tests scheduled, right? Like, and that was exactly because we don't even have time for tests in here if we're going to cover everything. So, and we lost the week because of the freeze stuff. So I'm trying to find places that I can trim. And I'm thinking maybe change of variables might be a place that I might be able to trim. At worst, what I could do is ask you to watch a video on it, you know? And maybe vector fields and line integrals, maybe we can do that in one day, maybe. But my goal is to still try it all possible to get to the end of the class. We'll see.
The videos are pretty good.
Yeah, I mean, they're there, so I might have to utilize them later. We'll see. For now, our goal next class is to come in here next week and get into triple integrals in cylindrical coordinates and then spherical coordinates. So basically, just like when we were in Cartesian and 2-dimensional space, we said, hey, we can do polar, right? Polar is another way to move around in 2-dimensional space. In 3-dimensional space, there's actually several types of coordinate systems. You have Cartesian, which is your X, Y, Z, what we've been dealing with. But then we have cylindrical, which is a different type of system. And then we have spherical. And they all have their pros and cons. Like sometimes it's better to use spherical, sometimes it's better to use cylindrical, sometimes it's better to use Cartesian. Just depends on the problem. So we're going to do everything we've just done today in 2 new coordinate systems. That's the goal for next week. All right. The mini exam that I sent out is due on Monday, on the 12th. It's only 4 problems, and if you've done it, I mean, there's a few problems on there that are a little bit weird, but you know, if you ask me questions, I think I can lead you down the right way on that. All right, that's it. Have a good weekend if I don't see you before.
You too. Thank
Thank
you.
you, sir.